So we're still dealing with two-dimensional flows, and our focus is still on bifurcations. So here we deal with transcritical and pitchfork bifurcations. From the study of one-dimensional flows, the normal form for a transcritical bifurcation is x dot is equal to mu x minus x square. The normal form for a supercritical pitchfork bifurcation is x dot is equal to mu x minus x cube, and a subcritical pitchfork bifurcation is x dot is equal to mu x plus x cube. For two-dimensional flows, we get x dot is equal to mu x minus x square and y dot is equal to minus y, and that's for a transcritical bifurcation. X dot is equal to mu x minus x cube and y dot is equal to minus y, and that's for a supercritical pitchfork bifurcation. And x dot is equal to mu x plus x cube and y dot is equal to minus y, and that's for a subcritical pitchfork bifurcation. Note that in the y direction, the motion is always exponentially damped. So let's plot the phase portraits for the supercritical pitchfork system. X dot is equal to mu x minus x cube, y dot is equal to minus y, for mu less than 0, equal to 0 and greater than 0. So consider mu less than 0. Here the only fixed point is a stable node at the origin. So we'll have a relatively straightforward phase portrait. So plotting y versus x, we have a stable node at the origin. With mu equal to 0, the origin is still stable, but we have very slow algebraic decay along the x direction instead of exponential decay. This comes from the analysis and the intuition obtained from the one-dimensional pitchfork system. Now we look at mu greater than 0. Here the origin loses stability and gives birth to two stable fixed points located at x star y star is equal to plus minus the square root of mu 0. One can actually compute the Jacobian at each point to confirm that the origin is a saddle and the other two fixed points are in fact stable nodes. Now let's plot the phase portrait for the system. We've highlighted the saddle at the origin, and those are the two stable nodes. So that fills out the full phase portrait for this system. So we look at an example now. Consider the following system. X dot is equal to mu x plus y plus sine x, and y dot is equal to x minus y, where mu is a model parameter. Show that a supercritical pitchfork bifurcation occurs at the origin. Determine the bifurcation value mu critical and plot the phase portrait near the origin for mu slightly greater than mu critical. So here's the solution. Note that the system is invariant under the change of variable x to minus x, y to minus y. So the phase portrait will be symmetric under reflection through the origin. The origin is in fact a fixed point for all mu, and its Jacobian is a is equal to mu plus 1, 1, 1 and minus 1, which has trace tau is equal to mu and determinant delta is equal to minus mu plus 2. So the origin is a stable fixed point if mu is less than minus 2 and a saddle if mu is greater than minus 2. So this suggests that a pitchfork bifurcation occurs at mu critical is minus 2, but we still actually need to confirm this. We now seek a symmetric pair of fixed points close to the origin for mu close to mu critical. Now recall that the system is x dot is equal to mu x plus y plus sine x, and y dot is equal to x minus y. The fixed points satisfy y is equal to x, and so mu plus 1 x plus sine x is equal to 0. One solution is x is equal to 0, but we already have that solution. So suppose that x is small and non-zero, and we expand the sine term as a power series. Then mu plus 1 x plus x minus x cubed on 3 factorial plus order x to the 5 terms will equal to 0. So dividing by x and then neglecting higher order terms, one gets mu plus 2 minus x square on 6 is approximately 0. So there is a pair of fixed points x star plus minus 6 times mu plus 2 square root for mu slightly greater than minus 2. Thus, a supercritical pitchfork bifurcation occurs at mu critical is minus 2. If the bifurcation would have been subcritical, then the pair of fixed points would exist when the origin was stable, not after it had become a saddle. We need to draw the phase portrait near 0, 0 for mu slightly greater than minus 2. To do so, it's actually useful to find the eigenvectors of the Jacobian at the origin. So we make a note that a simple approximation is that the Jacobian is close to that at the bifurcation. So A is approximately minus 1, 1, 1 and minus 1, which has eigenvectors 1, 1 and 1 and minus 1 with eigenvalues lambda is equal to 0 and lambda is equal to minus 2 respectively. For mu slightly greater than minus 2, the origin becomes a saddle, and so the 0 eigenvalue becomes slightly positive. So now we can go ahead and plot the phase portrait for the system. So we plot y versus x. The origin is a saddle. And that now completes the phase portrait. We have a word of caution: because of the approximations, the phase portrait is only valid locally in both parameter and phase space. We end with some final notes. The saddle node, the transcritical and the pitchfork bifurcations are all examples of 0 eigenvalue bifurcations. The bifurcation occurs when delta is equal to 0, or equivalently when one of the eigenvalues equals 0. Such bifurcations always involve the collision of two or more fixed points. In this lecture, we discussed the transcritical and the pitchfork bifurcations in two-dimensional flows. Now, these are bifurcations that have counterparts in one-dimensional flows as well, and we note that the pitchfork comes in two variants, a supercritical and a subcritical. Now, if you want to construct the normal forms for these bifurcations in two dimensions, all you do is look at the normal forms for these bifurcations in one dimension and add the equation y dot is equal to minus y, and we'll have the normal form in two-dimensional flows for these bifurcations. So to that end, there isn't much of a conceptual leap of faith in going from one-dimensional flows to two-dimensional flows, except to mention that it eminently could be possible that the algebra actually gets much more involved in typical two-dimensional examples.